So this is 12.2a, talking about chords and arcs. So first thing we're going to do is show you what a chord is. So by definition, a chord is a segment that hits a circle at exactly 2 points, where your end points of your segment are on the circle. So a chord will look something like this. Okay, if this is A and this is B, we would call that chord AB. Yes, like a chord right there. Yes. Now, a diameter can be a chord as well, but a chord does not have to be, does not have to be a diameter. So this we would call chord AB, but there's also an arc represented here that relates to it, and that arc is this arc here, my green. We would call that arc AB, and the way you write it is AB with a little arc over top instead. So this is arc AB. The top one is chord AB, is how you would say it. So that's what a chord is. Yes, ma'am.
So I know there's a chord, there's always an arc. Or no?
Yes, a chord always creates an arc associated with it. Yeah. Okay, so here's the deal. There are four theorems I'm going to show you today, but the first three all make kind of a circular process here. So instead of writing three separate theorems, I'm just going to write one starting statement and then the three theorems that like finish it off. So all three of these theorems start like this. It says within a circle or in congruent circles. Okay, so within one circle or incongruent circles, three things that we know dealing with chords and arcs. Okay, the first one is that congruent central angles, and I will draw pictures of this for you in just a second. Congruent central angles have congruent chords. So if the central angles are the same, the chords are the same, as long as it's in one circle or congruent circles. The second one says congruent chords have congruent arcs. And then the third one says congruent arcs. We loop back around to that first statement again. Congruent arcs have congruent central angles. Okay, so you can kind of see how the one becomes the next, and it's very circular, which is fitting since we're dealing with circles. With these theorems, the converses are also true. What's a converse? If I say if A, then B, what's the converse of that? If B, then A. Okay, so the reverse of all three of those is also true. So if they have congruent chords, they also have congruent angles. If they have congruent arcs, they have congruent chords. If they have congruent central angles, they have congruent arcs. Okay, so you can say it every which way and it will be true. So I'm going to draw for you two circles just to show you how these work. And then we'll do a couple examples. God bless you. All right, so let's say this is the center of my circle, and we have a radius here, and a radius here, and a chord. I'm just going to duplicate that and put it here. Okay, so if this is AOB and this is CPD, based on what we're saying here, first of all, what is a central angle? right. So the center of the circle is the vertex, okay? So like right now, angle AOB and angle CPD, those are central angles, okay? So what our theorem says is if those two angles are the same, then the chords are the same, okay? So if I know that those two arcs are congruent, I also know that AB is congruent to CD, okay? That second one says if the chords are congruent, then the arcs are also congruent. So now that I know AB is congruent to CD, I also know that arc AB is congruent to arc CD, okay? And like I said, it's circular. So all you need to know is one set of those three things, and you know the other two are true also. So if all they told us were the arcs are congruent, you could say the chords are congruent and the angles are congruent, okay? So they all affect each other. With that in mind, if I give you a circle, this is example 1. Let's say I give you this circle and there are a chord here and there's a chord here. Okay, this is R, P, T, V, and D. And then we're going to draw in a chord from R to P. And a chord from V to T. Okay. So they're going to give you a picture that looks just like this. No numbers, no markings, just a picture like this. And they'll say, what can you conclude? So there is something from that last set of 3 theorems that we know is true already right here. Anyone know what that is? Yeah, Emma. RDP, right. So angle RDP and angle VDT are congruent. How do we know that? Oops. Not because it's congruent arcs. No. What? Vertical angles, right? Those are vertical angles. So RDP and angle TDV are congruent by vertical angles. Okay, so even though they didn't mark them congruent for us, we know they're congruent because they're vertical angles. So that's your starting point. Okay, if we know those angles are congruent, then what else do we know?
Doesn't that mean RDV is congruent to PDT?
Yeah, we would know that these two angles are congruent as well. That's still vertical angles. What do those vertical angles lead us to? What? Did you just say something, Gracie? Who said something? Someone said something. If you have congruent central angles, you have congruent chords and then congruent arcs from that, right? So we're going to say that RP and our chord VT, so chord RP is congruent to chord VT. Okay, because the angles are congruent, then the chords are congruent. And then we also know that arc RP is congruent to arc VT. Okay, so those two arcs would also be the same. So if the angles are the same, then the chords are the same, then the arcs are the same, then the angles are the same, then the chords are the same, then the arcs are the same. It's circular, it just keeps going, okay? So we know all 3 of those parts have to be congruent. Questions on that? Okay, I have one more theorem for you, and this is the one, yes, sir.
Can you also do arc RB is congruent to arc PT?
You can, because we said if we say that these 2 angles are congruent, then their arcs are going to be congruent also. So you could say that arc RV and arc PT are congruent. I just was showing you the relationship between all three of them, but that would totally work too.
Okay.
Yeah. Okay. The other theorem starts out the same way. Within a circle, not when, within a circle or congruent circles, chords that are equidistant, so the same distance, chords equidistant from the center are congruent. Okay, chords equidistant from the center of the circle are congruent. Remember in, I want to say it was chapter 5, when we were talking about things being, or the distance from a point to a line. Do you remember how that had to go? There was a specific, like how you measured that distance from a point to a ray or from a point to a line. Anyone remember that? No? It's always got to be perpendicular, okay? So what they're saying is if I have two chords like this, and then the center of my circle, and I go perpendicular to them, okay, so this is a right angle, and this is a right angle. What this theorem is saying is that because the distance to them, so we'll call this E, F, and G. If we know that EF is congruent to EG, then we know that AB must be congruent to CD. Okay, so if EF is congruent to EG, then AB has to be congruent to CD. So if the distance is the same, then the chord length is the same, okay? And vice versa. The converse of that is also true. If the chords are the same, then the distance to them is the same, okay? So I'm going to give you two problems here, two pictures of that. And these problems are so quick. Usually you can look at it and see it and it's done before you really even get started. Here it is. Let's say you have a chord and a chord. A segment here and a segment here. And here's what we know. We know that this has a length of A, a length of 6, a length of 5, a length of 5, and a length of 12. So you should be able to look at this picture and say A is 6, right? If the distance to them is the same, 5 and 5, then this being 12 and having 6 and A here, 6 plus 6 is going to get you that 12. Those two chords have to be the same. So A will be 6. And here's the other thing. It will always cut that chord in half. So even if you didn't have the 12 here, you could technically tell me right now that that's 6 and 6. Okay? If you knew the chords were congruent anyway. Questions on that? Okay, last one. Let's say you've got a chord and a chord. It's not my best picture ever, but just follow the rules of it. If this is your setup and they ask what is the length of AB, What's that going to be?
20.
It's 20, right? These two are marked the same. So 10 and 10, meaning this is 20. And because the distance to that chord is the same as the distance to that chord, because those are both 8s, then the chords themselves both have to be 20. So AB would have a length of 20. Okay? So it's a lot of just very quick look at it and see what your missing piece is. Any questions on that?